Hi everybody, this is Mr. Folly, and I am on the wrong page. I don't know how this happened, but I am. So, welcome to the key of this happy little dude. Uh-oh, my pen's went dark. I hope that's okay. Alright, so let's start working. Determine either the phase change or the term for the phase change, then determine if the intermolecular forces are weakening, breaking, or forming. So, this is going to be a solid to a liquid. Oh, man. This happened right before. Let me see what I can do. There we go. Okay. So this is going to go to a solid to a liquid is melting, right? So I'm never going to use weakening, just so you know. It's going to be breaking. So solid, breaking. Remember, it's gas, liquid, solid. And these are the strongest bonds, right? So, and they get weaker as you go up, right? So solid is strongest bonds, right? Okay, then the next part. Oops. Control Z. Let's see if I can make this look a little bit better. Boiling is liquid to gas, and liquid to gas, again, you're breaking bonds. Gas to liquid is condensing, and going gas to liquid, you're forming bonds. Okay. Something to gas is sublimation. That's going to be a solid to a gas is sublimation, and you're going to be breaking bonds there. Gas to solid is going to be deposition. And another word that works is sublimation. And if I'm going gas to a solid, I'm forming bonds. So notice whenever I go, let's look at it this way. As I go up, I break. As I go down, I form. So if I'm freezing, I'm going from a liquid to a solid, and that would be forming bonds. Determine if the energy going into a system or if energy is being released from the system for each of the phase changes from number one. Explain how the energy is being used in each case. So the case is going to be forming bonds or breaking bonds. So if I go from a solid to a liquid, that has to absorb energy, and that is going to break bonds. Break, absorb. Hey, how about that? For B, liquid to a gas is going to absorb energy. So again, liquid to a gas, looking at this, liquid to a gas is going up. It's going to absorb energy. That's going to break bonds. For C, gas to a liquid. Gas to a liquid, I'll put it in here, gas to a liquid, that is going to release energy, higher energy to lower energy, release energy, that's going to form bonds. From D, I'm going to go from a solid to a gas. That's going to absorb energy because I'm going to break bonds. Break, absorb, release, form. E, gas to solid and liquid to gas. It's got gas to solid and liquid to gas. So gas to solid, I'm going from high energy to low energy. That's going to release energy. Releasing energy forms bonds. Whoops. Liquid to solid is going to release energy, and that's going to form bonds. All right, so little reaction fun. So complete the following reactions and balance each one. So I'm going to have magnesium plus HCl yields MgCl2 plus hydrogen. Okay, so I have two H's over here, so I need two over here. That gives me two H's, that gives me two Cl's, and I'm all set. Zinc plus HCl. Zinc is always plus 2, so ZnCl2 plus H2. So that is, again, going to be, it looks exactly the same, right? So the coefficients are going to be the same. So I need two, give me two hydrogens and two chlorines. Well, that's kind of psychedelic. That's kind of cool. Magnesium plus sulfuric acid, Mg plus H2SO4 is going to give me MgSO4, that's an M, plus hydrogen. So notice we're seeing that a metal plus an acid is going to make hydrogen gas. That's the indirect comfort level with it. So notice metal plus acid will always give me a hydrogen gas. Okay, metal plus acid gives me an ionic compound and a gas. To make this balance, it is balanced. Hey, how about that? I like that. Double replacement reaction. All right, so a carbonate plus acid. So I want you to know that H2CO3, this was in the notes, is exactly the same thing as H2O plus CO2. Exactly the same thing, like your parents and Santa Claus. So just know that that's it. Magnesium carbonate, MgCO3, hydrochloric acid, and these are going to be double replacement reactions. So magnesium and chlorine are going to come together and give you MgCl2. And then I'm going to get H2CO3, but that's going to instantly turn into H2O plus CO2. And the reason why we know this is we'll get bubbles. Okay. Zinc carbonate, ZnCO3, hydrochloric acid again. Going to give me zinc chloride. Again, these 2's are because manganese zinc is +2, chloride is -1, and water and carbon dioxide we know. Magnesium carbonate plus H2SO4, a little different, is going to give me magnesium sulfate. Both are 2 for charge, H2O plus CO2. And it doesn't say that balanced, but I think it probably comes out balanced anyway, doesn't it? It sure does. Nope, it doesn't. I need a 2 here and a 2 here. All right. Hey, look, looks like somebody forgot what they wrote in there before the thing. Okay, so first balance the equation, then give the analytic equation for each reaction below. Finally state the solubility rule that tells us what the precipitate is. So first balance it. So I need 2 nitrates. I'll put a 2 here. Gives me 2 sodiums. That's balanced. Okay. So if I have this, I'm just going to use my knowledge of knowing what the precipitate is to do this. I couldn't decide whether to make a parenthesis or a oxygen. Okay, so what rule is this? Most OH negatives are precipitates. Okay. All right, next one. Okay, so the net ionic equation here, I made a gas and I made a water. These turn into ions. But first I have to balance it, right? So my carbons are good, my calciums are good, my sulfates are good, my hydrogens are good, my oxygens, let's see, 7 and 7. So this is balanced the way that it's written, so that's nice. So what I'm going to do is the sulfate is going to fall off on both sides, right? And the calcium is going to fall off on both sides. So I have, remember, this turns into ions. 2H positive plus CO3 negative 2 turns into, you may think H2CO3, but remember, H2O plus CO2. That's it. All right. So this is a weak acid, so that means together. We're swimming together. Okay, so NH4, that is balanced the way that it's written right now. Same number of everything. Really? Yeah. So this is the exact same thing. Oh, no, this isn't. This has to be written as ions. Oh, man. So this is going to be H, well, and I wrote the wrong thing here. H, C2, H3, O2 plus NH3 turns into the ions NH4 positive plus C2H3 O2 negative. So you don't have ions on both sides, so there's nothing I can do with that. Doesn't form ions, doesn't I'm making my own abbreviations. Doesn't conduct in solution. Weak electrolyte. barely forms ions, barely conducts, and that one is specifically weak acids and bases. So non-electrolyte are covalent compounds. Strong electrolyte, 100% ions. Soluble salts, and strong acids and bases. And they conduct. What types of compounds are non-electrolytes? Weak electrolytes, strong electrolytes. Guess who did that already? What types of compounds are non-electrolytes? Non-electrolytes are covalent compounds. What type of compounds are weak electrolytes? Weak acids and bases. Which ones are strong electrolytes? You can tell I made this and then I did this later. Strong acids and bases and soluble salts. Write the dissolving equation for the ionic compound being placed in water. This happens to us a lot. We get this wrong. I'm just turning it into ions. Sorry, plus 2 NO3 negative. Li plus 1 plus Cl negative. So the periodic table tells us those charges as well as the ions we learned. 2 NH4 positive plus SO4 negative 2. Draw a picture of a non-electrolyte in water, weak electrolyte in water, strong electrolyte in water. You draw include 5 particles of each. No need to draw water molecules. Okay, so it's a non-electrolyte. This is a covalent compound and it doesn't split up. So CH3OH, CH3OH, H3OH, CH3OH, CH3OH. Weak electrolyte in order. I'm going to have 1 ion. So H positive, C2H3O2. HC2H3O2, that's 2. HC2H3O2, that's 3. HC2H3O2, that's 4. 1, 2, 3, so I need 5. HC2H3O2, that's 5. NaCl, so I need 5 of those. Na positive, 1, 2, 3, 4, 5. Good. So all ions. No ions. And then when you're drawing these pictures, a weak electrolyte will have 1 ion, which would be very few. In the box below, complete a particle representation in diameter terms of water molecule with proper orientation around the calcium ion. So remember, this is the negative end. This is the positive ears. So 4 water molecules. 1, 2, 3, 4. There we go. Consider the decomposition reaction of hydrogen peroxide, breaking down into water and oxygen gas. Write the balanced chemical equation for reaction that occurs. H2O2 breaks down into water and oxygen gas. Okay, so I need to balance my oxygens. So I put a 2 here. That gives me 4 hydrogens. 2 hydrogens. 4 hydrogens. Now I have 4 oxygens, 2 oxygens, and 2 oxygens is 4. All right. Okay, so oxygen's a big one. So I need 1. Oh man, I've got 1, 2, 3, 4 of these. So I've got to draw. So if I have 4 of these, I should have 2 of these. I should have 4 of those. So I need 2 waters. So this is how I got 1, 2, 3, 4. And then I need 2 H2Os. No, I need 4 H2Os. 1, 2, 3, 4. Only I said 4. No, I got 4. All right. Consider the particle diagram below, where the balanced chemical equation takes place between Q and N. So that means that Q plus N2, right? N2 is diatomic, gives me Q2N. And the balanced chemical equation, so let's see, I would need a half of an N, and I would, well, let's see here, if I had one of these, oh, let's see here. So Q is the dots, so I would need two of these, half of these, right? Because it would take half of this, one, that's what I'm making, to make one of these. So I don't like fractional exponents, so I would go double everything, 4, 1, 2. And there you go. Which is the limiting reactant, Q or N. So my limiting reactant I ran out of. My limiting reactant is ran out. Okay. Consider the particle diagram shown below. Write the balanced equation that takes place between Q and N. So Q plus N2, and again it's N2 because it's a diatomic dude there, is going to give me Q4N2. So I need 4 of these and 2 of those to give me 1 of those. Right? I don't need the 1, so it's bad form to put the 1, so I'm going to eliminate it. Student claims particle diagram on the previous page represents a perfect stoichiometric ratio. Do you agree or disagree with the student? Should have a question mark on it. Let's see here. See if it's not just a mistake. 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 Qs, and I have 2 of those, and that would give me, oh, whoops, I forgot this would have a 2. So if I did the balanced equation for that one, shame on me. I forgot to reduce it. Hey, caught my mistake. 2, 1, 1. So that would be a perfect stoichiometric ratio. Yes. No leftovers. Shown below are the reactions for the unbalanced chemical reaction. Q plus NQ yields NQ. Draw the particles in the after reaction box. Okay, so NQ would be one of these and one of these. Okay, so this, when I balance it, would be 2 and 2. Okay, so 2 Qs. So that's 1, 2. So draw that. Well, that's what I should do. So there's one of those and there's 2 of those. All right, I got to break up another one of these. 2 of these. These do not have to look as perfectly neat and in order, but they do. And then this one, honestly, it wouldn't break apart because you're not going to have leftovers. So what you're going to have, because you're not going to split up one of these. So I've got 3 of these left over. 1, 2, 3, and I have 2 of these left over. 1, 2. So I cannot have a single one by itself. No. Okay. Those just can't happen because it's not diatomic. Okay. When a physical change occurs in molecules, what types of bonds are involved? Intermolecular, intramolecular. Intermolecular. Explain. No new substances. So intra can't change. According to the balance equation below, how many moles of HI would be necessary to produce 2.5 moles of I2? Starting with oh man, really? Okay, so how many moles of HI would be necessary? So that's what I'm figuring out. Starting with 4 moles of KMnO4 and 3 moles of this. Okay, so this would make 5 times as much. This would make 20, and this would make 10 thirds as much. Okay, so I'm going to write that out because I don't like my answer that way. So I'm going to convert both of them into the same. So 4 moles KMNO4, just not trusting myself today, times 2 moles KMNO4 and 10 moles of HI, which would give me 20, which is what I said, moles needed. And then 3 moles of H2SO4 times 3 and 10. It's going to cancel out. I knew my math was messed up. 10 moles needed. Okay. For H2SO4. So how many moles of HI would be necessary to produce 2.5 moles of... man, I did that wrong too. 2.5 moles of H2I starting with... man. That's what I get for not reading the whole question. So I really should have started with 5 moles of I2 and figured out how many moles of HI I would need. So this would be 5 moles of I2 and 10 moles of HI. That would be 10 moles. So 5, 2. I didn't want to start with 5. I want to start with 2.5. 2.5, sorry. So that would be 25 divided by 5, which would be 5 moles of HI needed. All right. I'm almost done. According to the reaction represented below, how many grams of aluminum are necessary to produce 0.5 moles of hydrogen gas? So how many grams of aluminum are needed to produce 0.5 moles of hydrogen? 0.5 moles of H2 times 3 moles of H2 using my coefficients. And I want to find grams of aluminum. So first moles of aluminum. So 2. So I want to get that into grams, times 1 mole of aluminum, and we're calling that 27. So I can do this with a calculator. 0.5 times 2 is 1. 1 times 27 is 27. 27 divided by 3 is 9 grams of aluminum. And it doesn't really matter how, that doesn't matter because a mole is a mole is a mole is a mole is a mole. Okay, how many do I have left? 1, 2. Okay, I could do that, I think. According to the balance equation below, how many moles of CO2 are needed to react completely with 20 milliliters of 0.20 molar? Okay, so moles equal MV. So 0.2 times 0.02 is 0.004, 0.004, and that is moles of KMNO4. How many moles of ClO2? Okay, so 0.004 of KMNO4 times 4 moles. Okay, so here's where it gets tricky. MnO4 negative. You've got to be able to see that this is KMNO4, and they got rid of the K because it's always soluble. Okay, and then 3 moles of ClO2 negative. It's the net ionic thing that nobody likes. So 0.004 times 3 divided by 4 is 0.003. According to the equation below, whoops, my little box went away, or didn't go where I wanted it to. How many moles of potassium chlorate must decompose to generate 1 liter of oxygen gas at standard temperature, according to the equation above? So how many moles of potassium chlorate? So this is going to be KClO2. Whoa. Well, that's chlorite. We're going to guess that that's what we're going to go with. Oh, I didn't see the equation. Here's the equation. Here's my problem. I missed the equation. According to the equation above, how many moles of potassium chlorate must be decomposed to get 1 liter fraction gas at STP? So I'm going to figure out how many moles that is. So PV equals nRT. STP, the pressure is 1, volume is 1 liter. N is what I'm solving for. R is 0.08206. Standard temperature is 0, which is 273. Rearranging for that, I have 1 divided by 0.08206 divided by 273, and I get 0.0446 moles of O2. How many moles of potassium chlorate must decompose? So that's moles of O2. I'm going to change that moles of O2 into moles of KClO3, 2 and 3. Oh, my goodness. So on this, this is where it is. You can now use the calculator for it, but I'm just going to put all these in here. Times 2 divided by 3. It's a lot more annoying now. 0.0297. So, and 0298. So I'm just going to throw these in here. I'll make sure. How many moles of potassium chlorate? Yep. So I'm just going to put those in there and figure it out. 1 divided by 3 times 1 divided by 22.4. Not this one. 1 divided by 2 times 1 divided by 22.4. 0.0222. Nope. 2 divided by 3 divided by 22.4. 0.02976. Boom. Acetic acid and sodium bicarbonate reacted and the gas is collected. Determine the volume produced when this many grams reacts with that many milliliters. So first I'm going to make this moles. Moles equals MV, which is going to be 0.875 times 0.055. Notice I'm changing this into liters. 0.875 times 0.055 is 0.0481 moles. Notice how it's important to label it. Acetic acid, HC2H3O2. And notice I have grams of this. So I'm going to determine the volume of CO2 produced. So I'm going to convert it into this. And I'm going to convert this into this. Okay, so I'm going to do both of these into moles, and then I'm going to pivnerd it. Okay, so times, it is balanced, so 1 over 1 for moles. So that's going to be 0.0481 moles of CO2. And then I'm going to do NaHCO3. I'm going to change my color here. And I'm going to do 2.5 grams of NaHCO3 times grams of NaHCO3. I'm going to go to the periodic table to get that. And 1 mole. And then I'm going to have 1 over 1 for my moles again. And this will give me moles of CO2. So molar mass of that 22.99 is sodium plus 1.01 plus 12.01 plus 48. 84.01. So 2.5 divided by 84.01 is 0.0297. Okay, so looking at this, this is the actual amount because it is smaller. Now I'm going to find the volume of it with PV equals nRT. The pressure at STP is 1. Volume is what I'm solving for. Moles are 0.0297. R is 0.08206. T is 273. 0.0297, I'm leaving my calculator number there. 0.08206 times 273. And I get, the devil's number, 0.667 liters. Identify the limiting reactant and excess reactant from above. Limiting reactant is NaHCO3 because it made the smallest excess reactant is HC2H3O2. It made the most. What mass of sodium bicarbonate is required to produce 19 liters of carbon dioxide at that number and pressure? So, what mass of sodium? So 19 liters. Okay, so I got to find that moles. PV equals nRT. The pressure is 1.2. The volume is 19 liters. Looking for N. R is 0.08206. Temperature is 20 Celsius. 20 plus 273 is 293. N is 1.2 times 19 divided by 0.08206 divided by 293. I get 0.948. CO2. What mass of sodium bicarbonate is required? So again, we're talking about equal moles. Okay. So that equals the moles of NaHCO3. So I did that molar mass up here before. So 0.948 moles NaHCO3 times 1 mole over 84.01 grams NaHCO3 and times 84.01, I get 79.7. And I hope that's my last question. It is. So after having said that, I will say to you, toodles.